Another important coordinate system to learn is spherical coordinates. Now there are three spherical coordinates, and those are rho, theta, and phi. So this thing that looks like a P is actually a lowercase Greek letter rho. We're familiar with theta. And this letter is phi. And you'll sometimes see me write kind of a cursive version of phi. Those are the same letter. So this is kind of a cursive version of that letter. So just like I sometimes write theta this way. So you may see theta written either of these forms. You may see me write phi in one of these two forms. Now to give you an idea of what rho, phi, and theta are, let me show you in this diagram. Rho is the distance of a point to the origin. So rho is how far this is from the origin. Now you can contrast that with r from cylindrical coordinates. R is the perpendicular distance of the point to the z-axis. Rho measures how far the point is from the origin. Theta is exactly the same in spherical and cylindrical coordinates. So if I drop this point down to the xy plane, then theta, once again, is the angle between this rectangle and the positive x-axis, or the xz plane. And last of all, phi is the angle that this ray makes with the z-axis. So let's see if we can translate between rectangular, cylindrical, and spherical coordinates. One thing I'd like to do is draw out this triangle. It doesn't look like a right triangle, but it actually is, because remember, r measures a perpendicular distance to the z-axis. So if I copy out just that triangle, then rho is the hypotenuse of the triangle, r is this leg, and z is this leg, and phi is that angle right there. So from that picture, notice that sine of phi is opposite over hypotenuse, which is r over rho, which tells us that r is equal to rho sine phi, and cosine of theta will be adjacent over hypotenuse, which is z over rho. So z equals rho cosine phi. So remember, in cylindrical coordinates, we have x equals r cosine theta, y equals r sine theta, and z equals z. In our new spherical coordinates, if we replace r with rho sine phi, we get x equals rho sine phi cosine theta, y equals rho cosine phi sine theta, and z equals rho cosine phi. Oops, I wrote cosine and sine. So let me read those again. X is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. And you really do need to memorize both of these. Cylindrical is probably easy to memorize because of how similar it is to polar coordinates. This one's a little bit tougher. I'll let you in on the way that I think about it when I have to write it down. Working from top to bottom, I go rho, 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 then bottom to top, cosine phi, sine phi, sine phi, then top to bottom, cosine theta, sine theta. Rho, 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 cosine phi, sine phi, sine phi, cosine theta, sine theta. That's just my mnemonic. You might come up with something that works better for you. Now, before we do some examples or some ways of remembering, of thinking about what rho, theta, and phi are, I do have a bit of bad news. And that's that physicists reverse phi and theta. So they call this angle theta and this angle phi. That doesn't make any sense to us because we're so used to describing this angle using polar coordinates, and we call it theta in that situation. And I'm pretty sure that the physicists still call this guy theta when they're doing polar coordinates, but when they do cylindrical coordinates, they call this angle phi and this angle theta. Long-going debate. I don't know when they're going to come around. But anyway, in this class, this is the way it's going to be. But if you look up formulas in the back of your physics book, you might find that they have all the phis and thetas swapped. So, let's think about what phi is. Phi is the one which students have the most trouble getting their head around. So let's practice with phi a little bit. So remember that phi measures the angle away from the positive z-axis. So if phi is equal to 0, then that means that you're pointing directly up the z-axis. So if phi is 0, you get the positive z-axis. Let's see what happens if you set phi equal to pi over 4. So in space, here's the z-axis. We want all the points so that when we connect them to the origin, we're going to be at an angle of pi over 4 away from the positive z-axis. But these points can be anywhere in a circle around the z-axis. So if I look at all the points that make an angle of pi over 4 away from the z-axis, notice that I get the upper half of a cone making an angle of pi over 4 from the z-axis. So this gives us an upper half cone. If phi equals pi over 2, these are going to be all the points that are an angle pi over 2 away from the z-axis. So here's the z-axis. Here's pi over 4 away from it. If I go to pi over 2 away from the z-axis, then I'm in the xy plane. So pi over 2 is the xy plane. So I go from 0 to pi over 2. Notice that I'm sweeping out the points that are above the xy plane. Continuing, if I let phi equal 3 pi over 4, then I'm going, here's 0, pi over 4, pi over 2, 3 pi over 4, is going to give me the lower half cone. And finally, if I let phi equal pi, then I've traveled all the way from the North Pole to the South Pole. So phi equals pi is going to be the negative z-axis. So notice if I have any point in space, I'm going to be able to describe its phi using some angle between 0 and pi. So I start from the origin, the North Pole. If it's near the North Pole, then it's going to have a phi which is close to 0. If it's horizontal, that's going to be a phi equals pi over 2. Down there, it's going to be getting close to pi. If it's directly below me on the negative z-axis, then its phi coordinate is going to equal pi. So if I want to sweep out all of space, then it suffices to let phi go from 0 to pi, to let theta go from 0 to 2 pi, and to let rho go from 0 to infinity. Now, if I fix rho, then I'm going to be looking at all the points, let's say rho equals a, I'm going to be looking at all the points whose distance from the origin is equal to a. Well, in other words, that's going to be a sphere of radius a. So if I, for example, wanted to describe only the lower hemisphere, then I'm going to be taking points which are below the xy plane. So that means I'll be letting phi be going from pi over 2 to pi. And I'll let theta go from 0 to 2 pi. So I'll be going from pi over 2 to pi, which sweeps us out from the xy plane to the south pole. And then by letting theta go from 0 to 2 pi, I'm sweeping this all the way around. And that'll give me the lower hemisphere. On the other hand, if I wanted just the first octant of the sphere, so the part where x, y, and z are all positive, let's think about what the bounds would be. Since all these points are above the xy plane, phi is going to go from 0 to pi over 2. Remember, phi equals 0 is the north pole, phi equals pi over 2 is the xy plane, so I stop at the xy plane. And then I'll let theta start at 0 and also go to pi over 2. And that's what keeps me in the first quadrant in the xy plane.